Yeah. So to everyone who's joining right now, could you please put your year group in the chat while we're waiting? I'll just give people a few minutes to come in and then I'll get started at about 3 past. So yeah, I'll just wait a couple of minutes to start. Once it's hit 3 past, I'll just start. So it would be great if you could just put your year group in the chat. So I know what kind of audience I'm speaking to today. Should you do that for me? Fantastic. Okay, year 11, perfect. Well, anyone else who joins, they can just link in. In the meanwhile, let us start with today's session, which is on, well, let me do the introductions. So this is the last session of my GCSE Physics online school. And just to introduce myself, I'm Darina. I studied chemistry with molecular physics at Imperial College London University. And today we're going to be doing a workshop, well, a kind of discussion of series and parallel circuits, recapping the components in a circuit, looking at voltage, current, and resistance calculations. And then we're going to be doing a recap of the entire content that we've covered today. I've got some questions or a Kahoot, depending on how it turns out. Right, so let's jump straight into a little revision of circuits, how they work, the equations that we already looked at in our first lesson, and the naming of the components. So first things first, we've got our circuit symbols. So starting off with the first one, what do you think that is? If you could just type in the chat what you think that first circuit symbol is, and then we'll do the same for all of them. Just have a go. I'm not too worried if you get it wrong. So I think I'll probably give a couple of minutes. If you could put your ideas in the chat, that would be really great. No thoughts? Well, okay, what's at least the difference between the first one and the second one? Well, they've both got that left right sort of longer strip than the shorter strip on them, but on the left that is actually a battery, but on the right one that is a cell. And how we tell them apart is because a battery is made up of multiple cells, and so it just has more strikes like that. They're different only in name. They both can be used as a power supply. Now that third one, again, I'll just give a minute for you to think, and then I will put the correct answer up. So it's just a rectangle, no strikes through it or anything. Excellent. So that one's going to be a resistor. Perfect. So we'll have a little look at resistance later on as well. But for now, just know resistor, rectangle, nothing else. Right. One lower down, the circle with a cross through it. What's that one? And we were choosing from the names on the right-hand side. Right, a light bulb, perfect. We've got a bulb. So anything that sort of emits light is probably going to be roughly sketched like that. Next one, we've got a circle. I'm not sure why it's black. It usually isn't in circuit diagrams. We've got a circle with an A in it. An ammeter, perfect, yes. And it measures current, and we'll be looking at them again later on. The next one, what is it? The one with a V in it. Again, I'm not sure why it's black. A voltmeter, again, it's a measurement apparatus. This one is for voltage. And again, we'll recap this later on, but voltmeters are connected in parallel, ammeters in series. So we're doing a lot of work on series and parallel today and the distinction between them. Right, next one, the one below, so over here. What's this one? Any ideas? We've only got a few left, actually. Oh, I should probably put them on. So this one is when it's open, the circuit is not full. The circuit is not complete. When it's closed, it is complete. It's not quite a diode. That one's the next one along, actually. This is a switch. So the switch just basically controls whether or not the circuit is complete. If you've got that open, there can't be any current flowing through this branch or this bit of the circuit or whatever. The next one is a diode. Now, I don't know if you were here for earlier sessions, but we talked about how the diode had this little arrow here to signify the direction of flow of current. So it can go this way, but it can never go that way. And you've got light emitting diodes, LEDs, which light up when they do have current flowing in the right direction. So that's what LED actually stands for. So that's the diode. Any idea what this one is? Have a go. We've only got a few left. Right, variable resistor, perfect. So that's a resistance with which you can change the resistance value for. Next one, this one. Kind of like our usual rectangle for resistors, but we've got this stuff going in with the arrows. An LDR, a light dependent resistor, perfect. Okay, this one. This one looks a bit like a resistor as well, but don't let it fool you. A fuse, perfect. Now, I thought I was labeling this one last time when you said variable resistor, but now I realize, of course, we were talking about this one. So they're fairly similar, right? But the one with the arrow through is actually the variable resistor. And now that's because that arrow represents it kind of being able to go up and down. With the thermostat, I'm actually not quite sure what this line means, but you just have to remember that actually this one is the thermistor and this one is the variable resistor. But well done. So that's the fuse. The little line in the middle there represents the wire that is going to be melting if you pass too high of a current through it. Okay, great. So that one's a fuse, that one's a variable resistor. Perfect. Okay, let's have a quick talk about resistance. And this is a bit of a recap of what we did when we looked at the equations. So Again, resistance is anything that resists a current, and it's measured in ohms, a unit named after this scientist. Okay, and the resistance of a component can be calculated using Ohm's law. Can you remember Ohm's law? It's just an equation. If you can remember, put it in the chat. Any ideas? So the Ohm's law contains resistance, voltage, and current. So you've got to link them together somehow. Okay, well, we actually had, or you have a triangle way of expressing it. So resistance equals voltage divided by current. So you've got VIR here. Yes, okay, or you can express it in terms of voltage equals current times resistance. Perfect. So that would be, if you're covering the top part of the triangle up, and therefore you get current times resistance. And that's Ohm's law. Yeah, great. So let's talk about resistors in series and parallel, since this is the main topic of the first part of today. So we've got the resistors can either be connected like this, which is what we call in series. Remember, series means they're connected one next to the other. There's no branches or anything like that. They're just all in one line. When we have resistors in series, we just add them together. So for that, so with its series and we add them together, what do you think the total resistance of this combination would be? Have a go. Any ideas if you just add them through together? Oh, you only have the two there. So it would be 10 plus 10. We're not taking into account these ones just yet. So 20, great. Now with the parallel, it's not as straightforward and you actually don't need to know how to calculate it numerically, but you do have to be aware of the fact that it is much lower than in a series circuit. Now the reason for this is because there is more paths for the current to travel through. So it has more choices, therefore the resistance is going to be a lot lower. In this case, it's actually only 5 ohms, but you don't need to know how to calculate that. So don't worry about it. So that's the basic premise of resistance series in parallel. Well done. So we've got an example question. Have a read through. For question 1, using Ohm's law, and using the ideas we just discussed, what is the resistance of that bulb shaded in black? It'd be great if you could whip your phone out or a calculator, anything like that, and have a look. And since there aren't that many people here today, I'm very happy to give you as much time as you want to do the questions. If you're not sure though, just do type it in the chat because I will go through it. Don't want you sat there a bit confused about stuff. Remember, you're using Ohm's law. You've got the information that you need. You want a reminder of Ohm's law, I'll write it at the top here. Remember, we've got the little triangle here. So VIR. Okay, excellent. We've got an answer. What is the resistance to this bulb? So for the calculation here, yep, great. What you would do is obviously voltage divided by current, 10 divided by 2, that is going to be 5 ohms. Well done. So also, assuming all the bulbs are the same, what is the total resistance of this circuit? So we just said that this is 5 ohms. Excellent. What's the total resistance of the circuit? Excellent. 15 ohms because they're in a series circuit, so you just add all of them together. All right. Let's do just a couple more examples. So we've got to find the resistance of all of these bulbs. Well, this one's just the same, so let's not really do this one. Question 1 is exactly the same. We use the same ideas. So V over I equals R. So that would just be 12 divided by 3. But let's try the other two. So question 2, try question 2. So here again, we're working out this light bulb. And I'll just label that this is 6 volts as well. And we'll recap that again. So this is 6 volts across here. So what do you think? Just using the equation. For question 2. So we're just thinking about what the answer is to that light bulb there. Using the equation or your triangle, you've got to work out what the resistance of that light bulb is. Please have a go. Any ideas on that? Well, again, we use our equations. We use VIR, our triangle. We're covering up the R, so we know we have to do V over I. And that means that, again, we do 6 over 3, which is 2. So 2 ohms is the correct answer here. Okay. Now let's have a look how current and voltage behave in parallel and series circuit and how they work in general. So we've got current in a series circuit. How does it work? How does it split? How does it behave? Well, we know how to deal with current in a series circuit. We know, so if the current here is 2 amps, then that means that the current pretty much everywhere is 2 amps. So what do you think the current through the battery would be? Any suggestions? What's the current through the battery if the current at the beginning of that circuit in the wires? Right, 2 amps, perfect. What about, right at the end of a circuit? Yep, it will be 2 all around, perfect. And even in the middle, it will all be 2 amps in a series circuit. Right, okay. So in other words, the current in any series circuit is the same at any point. What about in parallel circuits? So in parallel circuits, we have a choice of routes. So we have a bit of a different setup here. So here's a parallel circuit. It has 2 branches. So we count it as a parallel circuit. So there's a second branch at the bottom there. If the current comes along, and as usual, it goes down, at this point, it's all the same, but it now has 2 paths to go down. And actually, current in parallel circuits splits at junctions. So half of it, assuming the bulbs are all the same, half of it will go down here into the middle path, and then half of it will go onto the bottom path. And this is assuming that all the bulbs are the same. If we had different bulbs, we would have slightly different ratios, but the key idea is that it still splits over the branches that we are taking. Right, okay, great. So again, in a parallel circuit, if the current here is 6 amps, what do you think the current here will be? Okay, so you've got 2 amps there, perfect. And that's exactly right, because what it does here, what the current does is obviously splits across these 3 circuits, so 3 branches, right? So we've got 2 amps, and 2 amps at the bottom as well. So that's current in parallel circuits, right? And what would the current at the end here be, that last arrow? Okay, 2 amps. Well, it's not a series circuit, is it? It's not the same all around. So we've got 6 amps at the beginning, and it wouldn't be 2 amps at the end, because can you see how all of those branches rejoin? That means essentially that all the current starts flowing together again, and we've got 6 amps at the end as well. So we start off with 6 amps, we split off into 3 branches, all of 2 amps, and then we have 6 amps at the end as well. Okay, we've got some example questions on this now. So if I place ammeters there and there, and I get 3 amps on the left-hand one, how much current do I have flowing through each light bulb? What would it be? Excellent, 1, because we're dividing it by 3. What about the second one? And the first branch, what would the current be? What do you think the current would be? Right, so we've got an answer of 2. Excellent. And what about in the second branch? Oops, sorry. So for that 2, did you mean that for the top one or for the bottom one? Let's talk about what the difference is and say which one is right. So actually the current for 2 amps here would be the bottom one. Let's think about this. And which branch would have the higher resistance, the top one or the bottom one? The top one would have the higher resistance. Well, the top one only has 1 bulb, and remember, each component that we have has a resistance. The top one would actually have a lower resistance. Now, if you remember Ohm's law, the lower the resistance, the higher the current. So instead of being like, okay, so my 6 amps splits 2 into the top one and 4 into the bottom one, actually more current goes where it's easier to flow, right? So if you take, okay, so I have my 6 amps, they're getting split up. Actually, when they split at the junctions here, it's not equally easy to go down each path. They take the easiest path, that's going to be the top one. So most of the current, 4 amps, goes in the top branch. If that's the case, how many amps goes down to the bottom? 2, yeah, that's correct. And you can do this with calculations later on when we talk about voltage. We'll do some examples, don't worry about that. Okay, so a bit of recap on voltage. Let's remember what voltage means before jumping into how it works in series and parallel circuits. So what does voltage mean? Can you provide me with any kind of definition for it? What's the definition of voltage? Just any kind, maybe you're using an equation or something like that, or just the best shot you can give it. What would be our definition of voltage? Well, we have an equation to define voltage, don't we? We have got, oops, I didn't put it on here, but the equation to define voltage, remember, is E over Q, the change in energy per coulomb of charge that is being lost or gained between 2 points. You can also define it in terms of work done, because remember, energy transferred is the same as work done. So it's essentially the work done per unit of charge, per bit of charge, moving this voltage, moving this charge between 2 points. So work done or energy transferred. Right, so let's think about voltage in a series circuit context and then in a parallel circuit context. So firstly, we've got voltage in a series circuit. For voltage in a series circuit, if the battery across if the voltage across the battery is 6 volts, can anyone answer what would the voltage be across this black battery that I've singled out at the bottom? What do you think? How does voltage behave in a series circuit? Any ideas? Right, great. So 2 volts. And the reason for that is because voltage in a series circuit, unlike current, voltage splits across the components. Current is the same everywhere in a series circuit. Voltage splits across the components, so it's not the same anywhere. So yes, you're completely right. Here we do 6 divided by 3. So we've got 2 volts across each of those bulbs. Well done. Okay, now let's have a look at why this is. So another interesting aspect is it's true that all of the voltages across a particular series circuit add up to be the voltage across the battery. Now, this is how we split it in the first place, but notice this is because the work done on each unit of charge must be equal to the capacity that the battery has for work, and therefore this is why we can use this hack of voltage across the battery equals voltage across the sum of all the components in the series circuit. Right, what if the resistances are different? So here we don't have a very neat split, so identical bulbs. What happens here if we've got a 10 ohm resistor and a 20 ohm resistor? Firstly, what would V1 read, that first one around the 10 ohms? This is using something again called ratio and proportion. So it still splits across the 2 components, but now it doesn't split evenly because the components aren't the same. So we've got one component of 10 ohms, one of 20. What would the ratio be that it's split in? And therefore, what's the voltage across that first 10 ohm resistor? Any attempts are very welcome. Right. So with this one, I think, so you're kind of maybe trying to learn from your mistakes in the past. With voltage, it's not the same as with current, right? Voltage, if you imagine, if the higher the resistance, the more work you have to do when you're moving through a particular resistor, right? So it's not like current. Current chooses the easy way out of life. Voltage actually has to do work to move it through the resistor. So for the first resistor, the voltage across it would be lower than for the second resistor because the resistance to the first one is lower. So what would V1 be? Give it another shot. It wouldn't be 40. What would it be? Any attempt? So you've split it in the correct ratio, I think, but just the wrong way round. So for this one, 40 would actually be the answer for the V2. And 20 would be the answer for V1. So if you wanted to do it in a calculation kind of way, you could actually use Ohm's law to do so. So let's have a look at how you can do that. So first you work out the total resistance, that's 30 ohms. Therefore, the current equals 2A. Remember, you're using your triangle, you're working out your current, that's going to be V over R. So V60 over 30 equals 2. That means the current in your circuit is going to be 2 ohms. 2 amps. And when you're going around, that means that the current flowing through the 10 ohm resistor, 20 ohm resistor, both going to be 2 amps, because we've just looked at in series circuits, the current doesn't change. Hence, the voltage across the first one, again, you're using the same formula. So you're using V equals IR. Therefore, you're doing 10 times sorry, V equals IR 10 times 2. And then for the second one, so let me just bring that up on screen. 2 times 10, that's going to be 20. And then for the V2, we're going to have 2 times 20, that's going to be 40. So there's two ways of doing this. There's the ratio method, which I talked about, which is you're thinking, okay, so the resistors are in a 1:2 ratio. So the voltage must also be in a 1:2 ratio and adding up to 60. So that's 20 to 40 volts. Or you can first work out the current using your Ohm's law and then apply it to each component in turn. All right, excellent. I hope you understood that. So the voltage across the bigger resistance is higher, unlike in the current example that we looked at before, as more work is done by the battery to get the current through it. You're using more energy, essentially. Right, perfect. So let's have a look at voltage next in a, so an explanation for that is, again, we have the same kind of setup, series circuit, except now the question is slightly different. So if the voltage across the battery is 6 volts, then what is going to be the voltage across these two lamp bulbs? Now, if this sounds hard, don't let it be. So really what this is asking is how much work do you have is done between these 2 points in a circuit, at which point, it's just the work done in the first bulb plus the work done in the second bulb. So if you want to have a go at so remember we calculated previously that the voltage across each component was 2 volts. What's going to be the voltage across the two components? I'll give you just half a minute to think about that. Okay, so if it was 2 across that first one, that means that we just add together the 2 volts from the first one, 2 volts from the second one. It means that we have 4 volts across those 2 lamp bulbs. So 2 plus 2. Right, fantastic. Secondly, we've got voltage. So now we're getting to our second stage of voltage, and that's voltage in a parallel circuit. Now, voltage in a parallel circuit behaves in a slightly different way to a series circuit completely. Basically, if the voltage across the battery is 4 volts, in voltage, we see that across each branch of that circuit, that's also going to be 4 volts. So let's have a look at that on the diagram. Each branch is 4 volts. We only have one component there. So what would be the voltage across that first branch? Have a little think and I'll get back in half a minute. Excellent. Yes, it would be 4 volts here. And again, with the lower one, that's just going to be the exact same thing because we've got our voltage being the same across all branches. Right, perfect. So we can make use of this with some rules that tell us how we can use series and voltage and series and parallel circuits. And to summarize, here they are. So for a series circuit, current is the same at any point and voltage splits up over each component. So if you took a random point in a series circuit, the current would always be the same, but voltage across each component is different. And then secondly, for voltage, we say that current, in a parallel circuit, we see that current splits up down each branch or each strand, it's sometimes called, but voltage is the same across each branch or each strand. All right, just one thing to mention here is that when you're looking at a parallel circuit, within the branches, that's treated like a series circuit. So if instead of the one light bulb that we have here, I had 2 light bulbs, so something like this, then we would have 2 light bulbs of the same resistance and the voltage across them individually would split. So across them both, we would still have 4 volts, but across each individual light bulb, what do you think it would be? So how many volts across each individual light bulb? Well, it's just going to split like a series circuit, right? So in a series circuit, we divide them up. They've got equal resistances, so we divide them equally. So we would actually have 2 volts across both of those light bulbs if they existed, right? Okay, I've got a bit of an example question for you here. It might look very complicated, but we'll do stuff in steps, so it's really not that bad. Let's have a look firstly at calculating the voltage across that lamp bulb. I'll give you a couple minutes. What do you think? Right, 3 volts. And how did you get that? So it's a bit of an unfamiliar setup, I know. It's not usually how we draw our parallel circuits, but it is fully available to us if we wanted to. And you will see past paper questions like this. Actually, what we see here is that this bit here, this top bit, is a branch in itself. And we have this bit here as the bottom bit, and that's a branch in itself. And didn't we say that voltage across every branch would be the same? So we've got 6 volts across the battery. That's going to be one branch. This is another branch. So what would the voltage be? Remember, the ammeter has very, very, very little levels of resistance, small levels of resistance. Any second thoughts then? If these are both branches and this is just one branch, only with the light bulb on it, we don't count the ammeter. What would the voltage be across that light bulb? Well, just the same as across any other branch in this circuit. This would be 6 volts, that voltage. Can you see that? Because you've got that battery here, that's 6 volts across it. This branch here, that's 6 volts across it. And then let's have a look at this branch with the voltages as well. So as we just discussed, overall, we've got 6 volts to split on that branch. But what would be in voltmeter 2? Any ideas? Because here, as you said, it does split into, we've got those 2 identical bulbs on the bottom part. What do you think? Any suggestions? What would that be? So remember, the total of them, V2 plus V3, is going to be 6 volts. And now, because they're the same light bulbs, you can say that they have the same resistances. And so the voltages across them would be exactly the same. So V2 and V3, they're going to have 6 divided by 2 volts, which is 3 volts on the bottom there. So V2 and V3 is going to be 3 volts. Okay, perfect. Let's have a little look at the currents as well. So we've got so far, we've got the fact that this is 6 volts, and we've got the fact that this is 3 volts and 3 volts. How is A1 getting on there? How can we calculate the current there? Again, just half a minute to think about this. So this top bit, ignoring all the extra stuff down here, this top bit really is just kind of a series circuit, but with a really weird load on here. So A1 is just in a series circuit. How do we work out current in a series circuit? We say that it's the same everywhere. So what will the current be in A1? Go on, type it in the chat. Don't be shy. What would the current be? It can be a bit of a guess. I'm allowing it. Any ideas? Well, that current be the exact same as on the other side of the circuit. We've got 3A here. It will be 3A there. So I hope you got that. As I said before, if you're unsure about a question, please do ask, and I'll go through it in a bit more detail. Right. Okay. So we've got the current now, and we can. So we've got the other two currents to find. Now we've now got a value for the voltage across that section, and we have a value for the current. We're trying to find a value for the current. So resistance is the same. So as I said, that's 3 amps because it's exactly the same wherever you go. Now, for that current, I want you to have a think about how you could measure it. You've got the voltage of that particular branch. What else do we need? Well, actually, we're using the resistance of an earlier part of the question. So here, the light bulbs still all just have a resistance of 3 ohms. So in this case, the voltage is 6 volts. The current is going to be, we're trying to find the current, are we? So we rearrange this equation, we go V over R, and that's going to be 6 over 3. So our final answer is 2A, 2 amperes of current. Right. Oh, I keep showing the answers. All right. So final thing to do is look at that last current down there. So I want you again to use the previous question to have a go at answering this one. What would A3 be? And again, using that idea that all the light bulbs are 3 ohms, etc., etc. Okay, well, we're using the same principle here because we know that the overall voltage is going to be 6 volts, but the resistance is going to be different, isn't it? The resistance is going to be times 2 or whatever that previous one was. And I'm telling you that previous one had a resistance of 3 ohms on each light bulb. So we've got, again, just using the triangle formula, we've got T divided by, sorry, we don't have T, we've got V divided by R, and that's going to give you the current, which is what we're trying to find out. So V divided by R, that's going to look like this. So that's going to V divided by R. That's going to be 6 volts because it's on a branched circuit. And then we've got on the bottom there, we've got our we've got our resistance of the 2 lamps all added together. So remember, that's the series part of the circuit. So we're just adding together the resistances caused by them. That's 6 over 6. So we get an answer of 1 amp. That's how you work out what you want to be doing, right? So 1 amp is the correct answer. All right. What else is it asking us to do? Okay, we worked all that out. Right, okay, perfect, well done. We've got a very similar question, but it's a slightly difficult. It's got the same concepts, exact same concepts as the question that I had. So could you please just, again, let's start with the low-hanging fruit. What is A1? How would you find A1? Well, again, we're dealing with current in a series circuit, right? So it would be the same as 3A, wouldn't it? So A1 equals 3A on the other side here. So we can write in the fact that it is 3A, perfect. So the next one that they probably want us to find is, again, the voltage across the light bulbs. So this time we have a rather different parallel circuit. I'm going to give you half a minute to have a little think about it. And what would that first voltmeter be accomplishing? You know, what reading is it doing? Okay, I hope you've had a go. It would be great if you just popped your answers in the chat, because then I know, whether to use a bit more time explaining or anything. But for that one, we have to think about the fact that there is now 3 light bulbs in the top row and 2 light bulbs in the bottom one. So again, we're using our equation. So we're thinking, okay, so overall in that branch, there's going to be 6 volts, isn't there? There's going to be 3 equal resistance light bulbs. So we just divide that by 3. We have 6 divided by 3 equals 2. Across 2 light bulbs, that's going to be 4 volts, right? So 4 volts across the 2. So V1 is going to be 4 volts. Again, I'm going to give you half a minute or something to have a look at V2 and V3. What do you think is going on here? So think about trying to work out the total resistance and therefore trying to work out the voltage that it splits as. So for the lower one, we only have 2 lamp bulbs in our bottom one. So we only have we have a lower resistance because we have fewer components. Now, could you have a go, please? Tell me, where would you expect the current to be bigger, in the top one or the lower one? What do you think, top one or lower one? Well, as we said before, the less resistance there is, the more likely it is for the current to go down that path. So because our lower one has fewer components in it, it's going to have less resistance and a higher current. Besides that, we've got our voltages again. So this time we've got 6 volts across that entire branch, but it's only shared with 2 light bulbs. So all we have to do is do 6 divided by 2. That's going to be 3 volts here and 3 volts there, because they're the same. And so that's going to be our V2 and our V3. Now, the final thing we need to do is therefore work out currents. And for this one, you always use Ohm's law as well. So you do V equals I over R, or however you choose to, sorry, V equals IR, or however you choose to remember it. And for the first one, again, I'll give you half a minute to maybe do a calculation or something, jot something down. So I want to now find the current through the top branch. So the current is going to be, okay, let's think of our equation. Current equals voltage divided by resistance. So here we have our voltage. Remember, our overall voltage is still 6 volts. No one's changed that. And then overall resistance, remember we said that these components were worth 3 ohms each. So in this case, we have our voltage, which is 10. Oh, sorry, I've still been working on the premise, and I didn't notice that this was 6. This wasn't 6 anymore, sorry. In that case, the ratio would be a bit different. We've got the same idea, but the voltages would be a bit different. They would have to be in ratios of 10 instead. So using that same logic, here we would have 6.6 recurring, right? Instead of as we had before, instead of 4 volts. And in these cases, it would be, 3. So here we just have voltage splitting in 2. So we'd have 5 volts for each, as opposed to 3 volts as the previous one. Okay, and, as I was explaining, you then use the equation to find the current. So 1.2 amps for the first one, 1.8 amps for the second one. And then, as I was saying, just a rounded version of our voltages. So you've got 6.67 for that one. And 5 volts for each of those because you have been putting them in the correct ratios. Okay, so that's all in this circuit. It looks quite scary, but when you break it down, it's not that bad. So things to take away from this: remember, current, the same everywhere in a circuit. So if you ever get a question like this one, this is really, really easy. You just put in the same value. When we get to branch circuits, remember that the voltage is the same across each circuit, and you can use either ratios to split it into the correct requirements, or you can use the equation to figure it out once you know the current. Okay, perfect. So we don't quite have enough people for the Kahoot today, so I thought that I would just finish off the lesson by looking at a few recap questions on all of the content that we've done so far. So again, it would be really, really great if you typed your answers in the chat, but basically what I'm going to do is I'm just going to go through and explain what the answers to these questions are and how to approach them. So just have a read through. I'll give you half a minute and then I will talk you through what's actually going on here. Okay, so in that first one, what's actually happening is that we have 4 resistors and we need to connect them so our resistance is as low as possible. Now, we went through today the idea that if you connect resistors in parallel, their resistance gets smaller. Well, that would be true in this case as well. And, you know, for 4 resistors, we would still put all 4 of them in parallel. We wouldn't lump in any with each other. So you have 1 resistor here in parallel. Here's your battery at the top. And we repeat it for every single resistance, because then our resistance will be as low as possible because the current has the most paths to choose from, and that is going to make the current higher and the resistance lower. Okay, so they should be connected in parallel, like in the diagram that I've drawn. Moving on to have a look at question B. Again, have a read through question B. So here we have 4 resistors connected in series with a 3-volt cell, as shown in that diagram. And we need to calculate the current that flows through the cell. Again, let's think of our triangle. So we have VIR. We're trying to find current, so we need voltage divided by resistance, right? So we need to remember that we're using the information from this first question to calculate the second one. So in the series circuit, we actually do know how to add together resistances. So now we're just doing 100 plus 100 plus 100 plus 100 to calculate the total resistance. So that would be obviously 400. And then for the current, we're putting that voltage at the start over the resistance at the end. So the current would actually be quite small. Excellent. We would have 0.0075 amps, or you can also think of that as 7.5 milliamps if you're using a prefix. Perfect. Yes, that's correct. So let's have a look at a slightly different one. So we've got another setup for the circuit in figure 3 here, and we've got an ammeter, again, actually displaying a reading of a very similar, similar current. And we need to calculate the potential difference across the 80 ohm resistor. So I'm going to give you a go at it, just half a minute, and then let's go through the question together. Okay, so we need to calculate the potential difference across the 80 ohm resistor. So for this, we actually don't know the resistance of all the resistors. So we can't use the sort of total voltage, but that doesn't matter because we have the current flowing through that particular side. So we can figure out, so we know that the current here is 0.075. From that, again, we're using our triangle. So this time we are finding the, so VIR, again, just as always, we're finding the potential difference this time. So we're doing current times resistance. So that number times 80. So the correct answer to this question would be 6. volts across this resistor. So that means that the remaining 4 volts must be split across the remaining 2 resistors. So, okay, we have then, we can then, if the question asks us to, calculate the resistance on that, but it doesn't. So let's have a quick look at question C. So if switch X is closed, then what will happen to the total resistance of the circuit? So I assume you've read through this, so let's just go through it. The total resistance of the circuit would decrease, right? Because again, as we've, yeah, great, it would decrease because as we've just talked about, this means that we've created an alternative pathway for that current to flow through. So it actually, most current would not flow through that 35 ohm resistor at all, because it simply doesn't need to. Current always takes the path of low resistance. Okay, calculate the new current through the circuit. Calculating that new current does require a knowledge of the total resistance of the circuit, doesn't it? So step by step, we need to be finding the resistance of that R, and therefore need to find, and therefore the total resistance of the circuit without that 35 ohm one, and find the new current. So to find the resistance of that, well, again, we find the voltage over that one. So the voltage before the switch was closed, the voltage over that component, same idea, current times. Right, so you found the voltage over that, okay. So, yep, great. So the voltage over that one is like this. And then for your other component, well, you're just making sure that they add up to 10. So take that away, so great. You've got 13.3 recurring. I want you to be careful with that because I think you've got maybe a power of 10 error. I'm not sure. The answer should be 1.37 for the voltage across that resistor. And from that, we can work out the, from that we are, no, all my working's gone. So what I was saying was 1.37 through that resistor, and therefore we can work out the resistance of it, so working backwards. So we can find that with that current that they're giving us, it's going to be a R equals V over I. So V is going to be the 1.37 divided by I, 0.075. So we know our resistance is roughly going to be, let's put it at 18.27 for your ohms. And therefore we can work through the new current. This is, we have our 2 resistances without the 35 resistor because that is no longer a compulsory part of the current to travel through. So we do total resistance is that plus 80. We're ignoring the 35 resistance. So our total resistance should be 98.26 recurring. Finally, we work out the new current, so our current actually, so it's no longer going through that resistor, so the total resistance of the circuit is going to decrease. The current will increase, therefore, because the total resistance decreases, and so our new current, that's going to be V over R. So we do 10 divided by that resistance, that is going to be a current of 0.1 roughly. I hope that has all made sense to everyone today. This was just a bit of a recap lesson and finishing off the parallel and series circuits aspects of electricity. Today is now the end actually of our GCSE Physics electricity revision session. So I hope you all got something out of them, and that is all from me today. I will stick around for just a minute if anyone has any questions. Apart from that, I hope you all have a great rest of the week. So if you have questions, just pop them in the chat.